Good morning, good afternoon, good evening, everyone. My name is Miska Hannuksela. I'm the head of video research in Nokia Technologies and a Bell Labs fellow. The topic of my presentation is the versatile video coding standard, application perspectives. Here's the outline of the talk. First, I will give a motivation why a new video codec was needed. Then I will give an overview of the versatile video coding standard as well as its development phases. The most part of my presentation will tackle the usage of VVC in applications. I hope that you will learn that the VVC not only is superior in compression, but also has additional benefits for applications. And finally, I will give you some takeaways. Starting with the motivation, why a new video codec was needed. The basic answer is that there's a lot of video traffic out there. Without better compression, the bit rates and picture resolutions would need to be limited. A new video codec provides the possibility to have a higher picture quality and resolution. Here's a prediction of the internet traffic. You can see that the amount of video traffic will grow from 2017 to 2022 by more than fourfold, according to this prediction. And also the relative share will grow from 70% to 80%, according to this prediction. Here's a similar graph for mobile data traffic. And according to this forecast, the amount of video traffic will grow from 2020 to 2026 by more than fivefold. And also the relative share will grow from 66% to 77%. This slide shows the video codec standards, the last couple of generations. First, there is the advanced video coding standard, H.264, which was finalized in 2003. Then following that was the high efficiency video coding standard, or H.265, standardized in 2013. And now the latest is the versatile video coding standard, or H.266, which was finalized in the middle of last year. In each one of these category codec generations, the target was to reduce the bitrate by 50% compared to the previous generation, while keeping the picture quality unchanged. All of these standardized codecs, they had a similar development focus. In other words, they aimed at the best compression for storage and also distributing video. And they are all suitable for a widespread use. That means a wide variety of applications. But they also had some differences, and particularly in terms of the resolution to which they were targeted at. AVC was targeted to resolutions up to high definition, HEVC for resolutions up to ultra high definition, and now VVC for resolutions up to 8K ultra high definition. In addition, there were additional content categories to which VVC was targeted at, including high dynamic range, screen content, and 360-degree video. In conclusion, each codec generation had somewhat different use cases and operating points that they were optimized for. Now, moving on to the overview of the versatile video coding standard. This first slide here shows the development phases. The development started with an exploration phase, which was done jointly in this joint video exploration team between ITUT Video Coding Experts Group and ISO IEC Moving Picture Experts Group. During that exploration phase, a joint codec software was maintained, and that was used to explore new coding tools. And it also served as evidence that was used to decide when to establish a standardization project itself. The standardization started with a call for proposal, which is a competitive phase where organizations can submit proposals of their own. The call for proposals had several categories: the standard dynamic range, high dynamic range, and 360-degree video categories. It had a good number of submissions and submitting organizations. At the end of this call for proposals, a subjective view and comparison was done, and a starting point was selected for the collaborative phase. And the starting point was decided to be a clean codec without many new coding tools, and then gradually coding tools were added during the collaborative phase. The collaborative phase started in April 2018, and roughly in every 3 months the experts met and had a very rigorous process to evaluate the proposals for the codec. During the process also, the standard draft was maintained and the codec software was updated with the adapted coding tools. At the end, the final decisions were made in July 2020, and then after editing period, the standard was finalized or released in August 2020. This slide shows the profiles of the VVC standard. Now, what's a profile? It's a subset of algorithmic features and limits that shall be supported by all decoders. A profile is specified to suit the needs for an application domain. In other words, usually not a single application, but a family of similar applications with similar demands. In VVC version 1, now there are 6 profiles, which have a sort of nested or onion shell structure shown here in this slide. Perhaps the most important profile is the main 10 profile, which can be assumed that most of the consumer electronics devices will support them eventually. It supports 420 chroma format and up to 10 bits per color component. There is a subset of that main 10 profile, which is targeted at still picture usage, still picture coding. That's called main 10 still picture. Then a superset of there are actually 2 supersets of the main 10 profile. The first called multi-layer main 10, which adds scalability with interlayer prediction. This can be used for a spatial scalable or multi-view scalable content, for example. Another superset is main 10 444, which adds a higher chroma fidelity. And there are also related coding tools. There's also a similar still picture profile for main 10 444. And finally, a superset of all is this multi-layer main 10 444 profile. Currently, the development of VVC version 2 is ongoing and will be finalized in January 2022. And it will include so-called range extensions, and it's envisioned that there will be 1 or more profiles with more than 10 bits per color component. During the collaborative standardization phase, objective metrics are used to compare proposals. However, after the completion of the standard, the performance of the codec is verified using systematic subjective testing, which is called verification testing. This slide shows the verification test results for those content categories that have been finalized so far. The anchor codec for these results is the HEVC reference software. And the VTM, the VVC reference software, was used in all the content categories. And then in the streaming category also, Fraunhofer HHI's WC Encoder was used. That codec contains perceptual optimization, and it's also much faster than the VVC reference software. The medium preset was used in these tests, which is more than 100 times faster than the VVC reference software. As you can see, in many content categories, the approximately 50% bitrate reduction target was met, and even exceeded in some of the categories, and particularly with perceptual optimization, very good results were achieved. Now, what's still ongoing is the high dynamic range verification testing, and spatial scalability testing is also under planning. You remember from the earlier slide that screen content coding was one of the development focuses of VVC. And that was chosen to be a focus because such content is common nowadays. For example, it can be used for game streaming or cloud gaming or slide or screen sharing in video conferencing. And then also many of the content categories actually include text and graphics that is overlaid on top of camera captured video. VVC therefore has coding tools that are inherently suitable for computer generated content, which are listed here in this slide. In some form, these coding tools also exist in HEVC extensions, namely the screen content coding extension or range extension. But here in VVC, they are now in version 1 and also included in either the main10 profile or main10 444 profile. In addition, VVC supports region-wise lossless coding, which is very handy, for example, to code texts or other important computer-generated content in a lossless manner, while the camera captured content can still be coded in a lossy manner. The results here are from the cited JVET contribution, and they show that 50% or even more bitrate reduction was reached with the VVC compared to HEVC main10 or main10 444 profile. Another interesting content category is the still picture coding. And here we have to notice that for still pictures, it's tougher to reach compression gains, since only the spatial redundancies can be utilized. VVC has been found to be a very good still picture codec, reaching close to 30% bitrate reduction compared to HEVC, as reported here in the JVET contribution. For still picture usage, then in order to have the metadata with the still pictures, the coded bitstream is encapsulated in high efficiency image file format, HEV. And HEV is a flexible image container format that can be used for any modern image or video codec. The key idea behind the development of HEV was to save space compared to JPEG, which was already defined or standardized in early 90s. The modern codecs typically support more than 8 bits per color component, which is a benefit, clearly. And then HEV also supports reversible image revisions like cropping and rotation without the need of transcoding the image. And HEV supports storing of multiple images in the same file, which can be used for advanced photography use cases, such as high dynamic range and exposure stacks for that purpose, or multiple simultaneously captured images from different sensors. HEVC nowadays is widely supported, for example, in Windows 10, Mac OS, iOS, and Android. So it's a good alternative to use video codecs that for image use cases. Then finally, some software implementations of VVC. As a summary, there are a couple of public source code packages that are available. I already mentioned about this WC by Fraunhofer HHI, which is optimized both for speed and has a very good compression performance. Also, its source code is publicly available. And there are also multiple real-time software decoders that have been demonstrated on smartphones and computers. And it has been said that even in low-end smartphones, one can achieve 720p real-time decoding, and starting from mid-range smartphones 1080p real-time decoding. These implementations have proven that the VVC standard design is mature and provides an excellent trade-off between compression efficiency and computational complexity. Now I'm moving on to the main part of my talk, usage of VVC in applications. And this section I have divided into two parts. First, I will have a brief overview of the communication protocol stacks that are used in I would say, major applications. And then I'm covering a couple of the VVC coding tools and their use in applications. Starting with the communication protocol stacks. This slide illustrates the stacks for different application domains, namely streaming, capturing to file and file playback, low delay applications such as video conferencing, and conventional digital television broadcast. While I'll skip the details, there are a few things worth noticing. First, VVC, like any other codec, needs a binding layer between the codec and the underlying format or protocol. For basic use cases, this binding layer can be quite thin in functionality, and then it becomes thicker for more advanced use cases. Second, when looking at the top left box here, you will notice that the streaming and file storage and playback use case use a common stack, which is based on the ISO-based media file format. And then for streaming, the ISO-based media file format files are time-wise segmented. The ISO-based media file format is also used for image storage. And on top of that is the high-efficiency image file format, which is derived from the ISO-based media file format. I'll then move on to the coding tools and explaining how they are used in applications. And I'm starting with a reference picture resampling coding tool. It can be used for streaming and low delay applications mainly, and mainly I would say it's targeted to 2D video. What does it mean? It means that the reference picture is resampled for interprediction. Here I have a simple example. So a chain of pictures, each one predicted from the earlier one. And here picture 3 is predicted from picture 2, which has a smaller resolution. And the RPR tool then implicitly resamples picture 2 so that it can be used as a prediction for picture 3. And this implicit resampling is integrated into subpixel interpolation, filtering of motion computation. From the high-level perspective, it's each picture has a scaling window And a scaling window covers the corresponding picture content at different times. And then a scaling ratio for the resampling is derived from the scaling windows. RPR can be used for several purposes. First, bitrate adaptation in video conferencing, and which itself can be used or be based on different reasons. So first is adaptation to changing network throughput or loss conditions, like a bitrate adaptation tool. Then a second is fast start. So at the beginning of a conferencing session, the very first picture can have a low resolution so that it is displayed quickly at the other end, and then gradually the resolution can be increased. And finally, in a multi-point conference, in the conference compose, the speaker who is talking can have a greater resolution than others. A second application domain for RPR is resolution and bitrate adaptation in streaming, which I will cover in the following slides. And then a third application category for RPR is spatial scalability, which I will cover also in subsequent slides. Now, RPR for adaptive streaming, and this slide shows some basic concepts of adaptive streaming over HTTP. The content is first encoded and stored in an origin server. Typically, the content is delivered over a content delivery network to one or many edge servers, and then based on the client's requests, then the content is delivered over the internet and access networks to the player. There may be multiple versions of the content, and the versions are advertised in a so-called manifest or media presentation description. In this example, we have 3 resolution versions of the content, which are all advertised in the manifest. So the player can actually select which content version it receives, and the selection can be done in a time-wise manner. So the player actually can estimate the throughput of the channel and then select the proper version so that the real-time transmission and playback without interruptions is achieved. In this example, it starts with HD, moves to 4K at the beginning, then afterwards, and then has to switch down to 720p. Now, in order to do the resolution switching, then each segment starts with an intra-coded picture or an independently decodable picture. This slide shows the how it is conventionally done. One example how it is conventionally done. So here at the beginning, the first decoded picture for a segment is independently decodable, IDR picture. This example shows a prediction hierarchy of 4 pictures, just as an example. Any prediction hierarchy can actually be used. And in the example, we have 1080p and 720p resolutions now shown. This kind of a structure we call a closed GOP prediction hierarchy, since there is no prediction between the segments at all. Now, how can HEVC improve this then? Is because it can use so-called open GOP prediction hierarchy. Again, there is an intra-coded picture here, which is now called clean random access picture. But in the first picture hierarchy here, these pictures are predicted from a picture or pictures from the previous segment also. And thanks to this by prediction of these pictures, then a compression improvement can be obtained. And this improvement has been studied in the cited paper here in two different settings: a live setting where a segment length of 1 second approximately was used, and an on-demand setting where a segment length of roughly 4 seconds was used. Two prediction hierarchies were studied, 32 and 16, which are quite common nowadays. And the paper found that that these kind of bitrate reductions can be achieved compared to closed scope prediction. Then the next slide actually shows what happens when a resolution switching is taking place in the segment boundary. So we are switching here from 720p resolution to 1080p resolution. And you can see that these raster pictures here are now predicted from the lower resolution prediction reference. And that prediction reference, it's a different prediction reference than what the encoder used. In other words, there will be some pixel value drift in these raster pictures. But the paper cited in the previous page, they also studied how to constrain that drift so that it's reasonable and hardly noticeable. So the drift is okay since it's only constrained to these raster pictures only. And also the decoder, since reference picture resampling is invoked implicitly, this bit stream is a normal VVC bit stream, so the decoder can perfectly manage that bit stream. Then moving on to the next coding tool, multi-layer scalability, which can be used in streaming and low delay applications, and can be used both for 2D video and 360-degree video. In VVC, the multi-layer scalability has been achieved with somewhat differently compared to earlier codecs. Particularly, there are no additional coding tools that are needed since interlayer prediction uses the RPR coding tool. Then a second difference is that only selected pictures are used for interlayer prediction as selected by the encoder. The encoder can select to use, for example, only the intra-random access point pictures of the reference layer or certain temporal sublayers only of the reference layer. The example here shows that only temporal sublayer 0 pictures are used as interlayer prediction references. And the decoder only receives the required reference layer pictures. Reduced complexity and memory usage compared to scalable extensions of earlier codecs is achieved because, first, no separate interlayer reference pictures are generated. Second, no additional coding tools or interlayer prediction tools are present. And third, the decoded picture buffer requirement is derived only from the pictures that are needed for decoding and received by the decoder. Multi-layer scalability in VVC can be used for any type of scalability, for example, spatial and quality scalability or stereoscopic and multi-view 3D coding purpose. This slide illustrates how we can use multi-layer scalability for video conferencing and streaming. We can compare multi-layer scalability to so-called simulcast, which means simultaneous coding of multiple single-layer bit streams. The bitrate of a multi-layer bit stream is less than the bitrate of simulcast bit streams in the uplink direction or when all the bit streams are stored. The bitrate of a multi-layer bit stream is more than the bitrate of any one of those single layer bit streams in the downlink direction. But this gap can be reduced by selectively forwarding only the base layer pictures that are needed for decoding in the VVC multi-layer bit stream. And that is shown here in the example. So we have the bit stream also presented in the previous slide, where only the temporal sublayer 0 is used as an interlayer reference. So this middle box here, somewhere in the network, does not need to forward the base layer temporal sublayers 1 or above to the receiver at all. So the receiver actually gets this kind of a bit stream for decoding, where only temporal sublayer 0 is present in the base layer. Another usage for multi-layer scalability, particularly for conferencing use, is to have unequal error protection for the base layer or for some of the sublayers. And this unequal error protection can be achieved by selective retransmission or forward error correction, or both. So the idea is to simply protect the base layer or some of the sublayers better than the other content, so that if there are some congestion or packet losses, then there at least would be some quality of the video to be displayed. Moving on to next coding tool category, gradual decoding refresh, which can be used in low delay applications, both for 2D video and 360-degree video. An underlying observation here is that video bitrate varies depending on the content and encoder choices. And particularly, there's a big difference in the bitrate for inter and intra-coding. Intercoded pictures are typically at least 5 times larger than intercoded pictures. On the right here, you see an example. So these peaks are intra-coded pictures, whereas the other pictures here are intercoded. So therefore, a key for low end-to-end latency is that the video bitrate should match the transmission bitrate as closely as possible, because otherwise there would need to be initial receiver side buffering to compensate the differences between the encoded bitrate and the transmission bitrate. In gradual decoding refresh, the intra-coding is applied gradually to avoid bitrate spikes of intra-pictures. And you can see here the orange curve is resulting from such gradual decoding refresh. In the next slide, I will show some more details. The gradual decoding refresh is not a new thing. It's at least 20 years old, but VVC is the first standard where all the decoders are required to support it. In the previous standards, it was optional for decoders to support. Here I have some more details. So in the encoder starts the gradual decoding refresh. It's in a so-called GDR picture. It codes an area, here a vertical stripe with intra-coding. And that is called a clean area, which is then gradually increased over recovering pictures until a recovery point picture is achieved, where the entire picture is then correct. In the GDR picture, there's also a dirty area, which is inter-predicted from pictures that come earlier than shown here in the slide. And a key thing is to turn off loop filtering between the clean area and dirty area. In VVC, we can use so-called virtual boundary, which turns off all the loop filtering in this indicated boundary. And this is done both in the encoder and in the decoder. In addition, the encoder needs to encode the clean area without prediction from dirty area. For example, the encoder avoids motion vector candidates originating from the dirty area and intra-prediction directions that would use pixels from the dirty area. So for example, here we have the white range here, which is predicted from the earlier picture. Then motion vectors also need to point to the clean area of the earlier picture. On the decoder side, the operation is simpler. So the decoder only needs to start decoding from a GDR picture. This picture from the dirty area can contain references to unavailable reference pictures, so they must be gracefully handled. And then the decoder also needs to start output at the latest here from the recovery point picture. Since there are some prediction constraints that the encoder needs to apply, GDR actually causes a bitrate increase compared to usage of intra-coded pictures. And the amount of increase was studied in this JVET contribution. It was found to be rather moderate and more dependent on the content or the video clip itself rather than the resolution. This demo compares intra-picture coding and GDR when a receiver joins in the middle of a video conference. The video at the top is showing the receiver operation with a bit stream that contains intra-pictures, and at the bottom is the receiver operation for GDR. There are two graphs, one showing the buffer level in the decoder's coded picture buffer, and another one showing the bits spent per picture. In the graphs, the blue curve is the intra-picture case, and the orange indicates the GDR case. You can see that the playback of the GDR video starts almost immediately, and the picture is gradually refreshed during the first GDR period. The demo shows the greenish dirty area during the refresh, exactly like it is decoded. A smart receiver can instead display a black dirty region, of course. For the bitstream with intra-pictures, it takes about 800 milliseconds to receive the first intra-picture, which is also the additional end-to-end delay or lag of the intra-coded bitstream, of the bitstream with intra-pictures, sorry. From the bits per picture graph, you can notice that the intra-pictures are indeed large, and that the GDR bitstream has a pretty stable bitrate. Okay, moving on then to the final coding tool, subpictures, which have a couple of use cases, but I'm demonstrating it here for a 360-degree video, and particularly for viewport-dependent 360-degree streaming. The underlying observation here is that when 360-degree video is viewed, the user only sees a portion of the video at any single time. And we need to stream that portion only in a higher quality, whereas the remaining video can be streamed at a lower quality and just for as a backup for quick viewing orientation changes. In tile-based viewport-dependent 360-degree streaming, The content is encoded with tiles, where tile is here defined as an independently decodable and extractable coded region, a little bit differently than what some of the video codecs define tile. Then multiple qualities or resolutions or bit rates are made available, and each tile stream is made available separately. So the player can actually selectively select which tiles are received. So different areas of the 360-degree video are then selectively received at different qualities. The benefits are that more than 30% bitrate reduction compared to viewport independent streaming can be achieved. And then if different resolutions are used, then a greater resolution on the viewport can be achieved compared to the overall decoding capacity. In this paper, for example, it has been shown that the content to the viewport can originate from a 6K resolution content, and whereas the decoding capacity was only 4K. Tile-based viewport-dependent 360-degree streaming was achievable with older codecs as well. In HEVC, a method called motion constraint tile set can be used, which simply means that the encoder avoids prediction dependencies outside MCTS. In VVC, kind of a layer called subpicture is added between the picture layer and the slice layer. Subpicture is a rectangular region that consists of one or many slices. And for this application purpose, the encoder and decoder treat subpicture boundaries like picture boundaries, which means that if a motion vector points outside of the picture boundary, even slightly, then the boundary pixel padding is taken into use. And that achieves some compression gains, which were studied here in this JVET contribution, depending on the tile size. A nice compression gain can be achieved. Another difference between HEVC and VVC for this application is how the tiles are merged into a single bit stream so that a single decoder instance can be used. In HEVC, that merging operation needed both parameter set and slice header rewriting, whereas in VVC, thanks to the subpicture design, only parameter set rewriting is needed. So this operation is much simpler in VVC. And finally, there is a difference in how the viewport change is responded. So in HEVC, a full picture refresh is needed, and in VVC, a subpicture-wise refresh, which I'm demonstrating in the following slide. So a full picture refresh just means that whenever there is a viewport change, as illustrated here, then the entire picture needs to be encoded in an intra-coded manner. But in the VVC case, only those subpictures where the quality changes need to be encoded in an intra-coded manner. And the remaining subpictures can then continue to utilize interprediction. This achieves some compression gain, which has been studied in this paper, when for content where there is no or slow camera motion, the compression gain is actually pretty big. Whereas when there is fast camera motion, intra-coding is anyways needed, so the compression gain was moderate. All right, then some takeaways for you. So as shown, VVC achieves about 50% bitrate reduction in many content categories compared to HEVC. And then I wish you to remember that VVC also has additional benefits in application usage, particularly in efficient resolution switching, the scalable video coding is achieved with reduced complexity and memory usage compared to earlier codecs. VVC has achieved slow delay operation thanks to gradual decoding refresh in all decoders. And finally, the subpicture feature provides inherent 360-degree viewport dependent streaming support. And there are also other 360-degree coding tools available in VVC. Thanks for listening.